Hello, in this course we are going to talk briefly about voltage regulators. I will cover voltage regulators in a more detailed fashion in the later courses, but now I just want to point out some useful informations that you should remember. Now let's go back a little bit to voltage rectifications, which is converting AC to DC current, right? By choosing capacitors that are sufficiently large, you can reduce the ripple voltage to any desired level. This brute force approach has three disadvantages. The required capacitor may have to be too big in size, which in turn will be expensive. The second disadvantage is that the short interval of current flow during each cycle produces more heating. The last disadvantage is that even with the ripple reduced to negligible levels, you still have variations of output voltage that are due to other causes, like for example the DC output voltage will be roughly proportional to the AC input voltage, giving rise to fluctuations caused by input line voltage variations. In addition, changes in load current will still cause the output voltage to change because of the finite internal resistances of the transformer, diode, etc. In other words, the Thevenin equivalent circuit of the DC power supply has a higher resistance than zero. A better approach to power supply design is to use enough capacitance to reduce ripple to low levels, perhaps 10% of the DC voltage, then use an active feedback circuit to eliminate the remaining ripple. Such a feedback circuit looks at the output, making changes in a controllable series resistor as necessary to keep the output voltage constant. This is known as a linear regulated DC power supply. I will talk about feedbacks like negative feedback or positive feedback in a future course, so don't worry about that for the moment, and I don't expect for you to understand. What you have to remember in this course is that these voltage regulators are used almost universally as power supplies for electronic circuits. Nowadays, complete voltage regulators are available as inexpensive ICs, like priced under $1. A power supply built with a voltage regulator can be made easily adjustable and self-protecting, like for example against short circuits, overheating, etc., with excellent properties as a voltage source, like internal resistance measured in milliohms. When an ideal voltage source has zero internal resistance, it can drop all of its voltage perfectly across a load in a circuit. Being that the source has zero internal resistance, none of the power is wasted due to internal resistance. The ideal voltage source can 100% efficiently drop all of its voltage across a load. This is proven by Ohm's law. According to Ohm's law, voltage is dropped across circuit elements according to the formula where the voltage is equal to the current times resistance. If a voltage source has zero internal resistance, it can drop all voltage across a load and none will be wasted internally. This is 100% power efficiency, and this is an ideal voltage source. Being that an ideal voltage source that has zero internal resistance and use 100% efficiency to outputting all of its voltage to a load due to perfect voltage division, its voltage output to a load is steady and constant and doesn't fluctuate even if load resistance values change. Thus, the voltage output by an ideal voltage source looks like this. It has no ripples at all. Unfortunately, ideal voltage sources doesn't exist, but the internal resistance of some high-performant voltage regulators can go all the way down to milliohms, which is pretty good, right? We will deal with regulated DC power supplies in the future, but for now I just want to show you how the output voltage looks like when we are using a voltage regulator. Alright, here we are. As you can see, we have a 5 volts AC source which is outputting a signal at 120 Hz. We have this part of the circuit, which is nothing else but our voltage regulator. I just didn't find an IC, so I had to build it on my own. We have these two resistors here, which is our negative feedback. Don't worry about that for the moment. And we have this 1 kilo ohm resistor here, which is obviously our load. This circuit takes a variable input voltage and outputs a stable voltage regardless of the current required by the load. So this means that even if I change the resistance of our load, the output voltage will remain steady at a constant voltage. This is a huge advantage, and you could not keep the output voltage as stable as here just by using a full wave bridge rectifier along with a filter capacitor. The other advantage is that we reduced the ripple voltage to minimum without even increasing the value of the capacitor. In fact, we don't even have one. Please note that in real-world applications, you will almost never see AC source connected directly to a voltage regulator. And this is because the majority of the electronic devices needs to be plugged into the wall outlet. So first you need to reduce that high voltage to a lower voltage using a transformer. You have to convert that to a DC current, filter it with a capacitor, and after that, if you want a stable DC voltage, you will use a voltage regulator.